Hey guys, welcome back to another fantastic chemistry video, and today I'm going to talk about alkenes, double bonds, fun things like that. Let's get after it. Introduction. Well, we all know that alkenes are hydrocarbons that contain a carbon-to-carbon double bond. Very simple, but very important. So here's the simplest of all the double bonds, all the carbon-carbon double bonds. Simplest of the alkenes. Now remember, double bonds contain a sigma and a pi bond. This is from a previous unit, so you should hopefully be thinking this looks very familiar to you. I'm doing it kind of fast because this is a little bit of a review. So remember, alkenes have a sigma and 1 over 2 pi up there, 1 over 2 pi down there. That's a double bond. That's an alkene. It's a sigma and a pi bond, and the pi bond is the weaker of the two bonds. Sigma bonds are very strong because they have good orbital overlap. Double bonds are, pi bonds are weaker because their orbital overlap is not as efficient, shall we say. Now, in double bonds, you can have what's called stereochemistry. Cis and trans. We're going to get into that a little more in a minute. Well, let's just take a simple molecule like this. Now, we've learned already in this class that single bonds can rotate and double bonds cannot. We didn't really get into the reason why double bonds can't rotate about the axis. When I say rotate, I mean rotate about this bond here. So this methyl group all of a sudden can't be down here on the same side as this methyl group. That just doesn't happen spontaneously in alkenes. They have to go through a chemical reaction. And why is that? Well, in order to go from here to here, you have to first break the pi bond. The pi bond itself has to break. Then you'll have freedom of rotation. So recall, and let me just do this as neatly as I can. So we have this pi bond right here. And here's the other items on the double bond. So here's our double bond, right? Now this is the trans double bond. In order for this to switch over to this, in order to get that thing to move, we have to break this bond so that we can rotate and then reform, okay? Now that has to be done chemically. There's no other way to do it. So you have to break this interaction here and here so that you can get now, this is where it's going to get a little bit snaky. I'll do my very best. So now the pi bond here, instead of being in the plane, is now going to rotate towards me, or in towards us. When that happens, the pi bonds, they will be going back this way and coming forward like that. And I'm trying to show now that this pi bond, p orbital here is at 90 degrees to this one because it's in the process of rotating. It's in the process of rotating. Because we broke this interaction, now there's only a single point of contact between these two carbons, so now the bond can rotate. And they will. If you break a pi bond, a double bond will rotate to go to the lower energy conformation. And eventually, once its rotation is all complete and stuff like that,